Nuclear fusion is what powers the sun. Cold fusion, it creates headlines, and some say it could power Earth's future energy needs. Indeed, 2 months have passed since researchers called a press conference at the University of Utah to announce that they had demonstrated cold fusion. Controlled nuclear fusion, that is, at room temperature, achieved on a tabletop in an electrochemical cell, a test cell containing the metals palladium and platinum immersed in heavy water. Now, scientists from around the world are in Santa Fe, New Mexico. They've come to this, the oldest capital city in the country, a city tucked at the base of the Rocky Mountains and located in a state renowned for its unique blend of culture and cutting-edge science and technology. They're here for a special workshop, the Workshop on Cold Fusion Phenomena, an event sponsored by Los Alamos National Laboratory under the auspices of the U.S. Department of Energy. There are data and ideas to share and discuss, and research directions to chart and clarify. This satellite broadcast is available anywhere in the continental United States. Join us now as the proceedings continue. Let's go live to the Sweeney Convention Center.
Testing.
In exchange for talking for a brief time, we get the brunt of a great number of questions. That's right. Say everything as confusing as possible for the rest of the time.
A request which we had Dr. Hackerman that I should say a very brief word about 3 concepts which keep on coming up from the electrochemical side.
People will not be able to see that with these lights on.
Okay.
The lights are shining right directly in everybody's eyes.
Well, you say it's all because of the cameras.
Yeah, we're looking
Yeah.
blinding lights up there.
Yes. Now, who's in charge of the lights? Is anyone in charge of the lights? Are you in charge of the lights? Well, they say they're working on it. I guess I'll do the best I can verbally. I want, first of all, to define what this word overpotential, which electrochemists use so much, means. I think there's a physics word for it. I think in physics you would call it bias potential. Now, what it simply means is that when the reaction, in this case the hydrogen evolution or deuterium evolution reaction, is in equilibrium, it is of course going in both directions at the same rate, and when you want to make it go netly cathodic, as we call it, or hydrogen evolving, electron doning to the solution, we say you increase the overpotential. We mean that you make the electrode more negative compared with a standard. That standard is the standard potential corresponding to the equilibrium. Overpotentials are around about 0.5 volts, 1 volt, that type of thing. And we have a relation. Now let's see. Going to yell at me? No yelling. Oh, no. Look, until we get the lights better, the only thing I can do is to do it this way. So what we do is to plot the overpotential that way, and the rate increases exponentially. Now the rate, that's the rate at which the hydrogens evolve, goes then 10 to the 10, 10 to the 12 times in range, so that by using overvoltages or overpotentials of the order of a volt, 1.5 volts, say, you can get very, very large changes in rate. Now that's a pure bit of electrochemistry. And when it comes to touch on the alleged fusion, which I much prefer to call the Fleischmann-Pons effect, then there is this concept called fugacity. Now, I'm not too sure that there are very many people in the room, including perhaps even the electrochemists, who are absolutely sure what fugacity is. And it sounds like something that you caught or something like that. Have you got a fugacity? And there is the relationship F equals P0. P0 is the external pressure, usually 1 atm, of course, and F is what we call fugacity inside the electrode. Inside the electrode. Now, for the moment, until I come back to this point, just think of fugacity as pressure. It isn't exactly that, and I'll deal with that point in a moment. What I want to get over with this is that with F equals P0 e to the minus 2, and that eta is the overpotential I talked about. F the Faraday, or the charge on 1 gram iron, RT is common ground, I guess, for both of us, with quite low overvoltages of minus 200 millivolts, 0.2 volts, or a reasonably halfway stage of 0.5 volts, you can get the most startling and amazing, quote, pressures, unquote, like 10 to the 12 atmospheres or something of that type. When all this broke, I called up Peter McIntyre at Texas A&M because I knew he was a fusion man, and I said, what's for fusion, what pressure would we need? And he said 10 to the 12 atts after a little calc. So I've always quote 10 to the 12 atts as something interesting, the fusion point of view. Now, the immediate objection to all this is if fusion, if fugacity and pressure are the same, won't the electrode have broken down or flown to bits or broken up or exploded long before we got to anything like 10 to the 12 atts or something absurd like that? And the answer is that's where the fugacity and the pressure comes in, because fugacity is a kind of ideal pressure, a little bit like what, and this is a physical chemical term, I agree, internal pressure is. And the relationship, which, by the way, I didn't have a book for this, I remembered this, roughly, I hope the figures aren't too wrong, something like this, that when the fugacity goes up to something like 10 to the 12, the pressure is way down at 10 to the 4. These are all atmospheres, 10 to the 4, 10 to the 5. And that's a not unreasonable pressure for the pressure inside a metal. You get yielding and spalling at 10 to the 4, 10 to the 5. But it would be possible, perhaps, to agree with fugacities of 10 to the 12 and pressures of 10 to the 4. So really those bits are the only things I wanted to say. They're introductory, and they just mean a kind of definitional introduction strictly for the physicists, or for 95% of you, I think. And if you want to ask me any questions about that right now, I'm ready.
rather high concentrations of tritium. And so we put together a team consisting of Roland Jalbert, who will be giving much of this talk, Bill Moss, and myself, and several other staff members and technicians to work on this project. They sent us 5 samples, which we received on Friday. 2 samples were of D2O, 1 which had LIOD in it, and presumably other small amounts of various poisons, a standard HTO solution, and samples from 2 of their cells. Roland, why don't you continue telling how we treated these?
Thank you. The second person on the list of 3 is Bill Moss, who heads the counting section of the bioassay group at Los Alamos. We did the counting at that laboratory because their counter had the ability to give us an instant spectrum of the beta, which we wanted to get very much because of the possibility of counting some bioluminescent or chemiluminescent material. So that was important for us, and we decided to do our counting in that laboratory. Those 5 samples came in early Friday afternoon. They were in scintillation vials that were sealed in wax, and with the quantities indicated on the view graph, which has disappeared upstairs. Oh, there they are. Okay. And our approach with these small quantities of material was to neutralize the samples that had LIOH or LIOD and expand the volumes to something that were reasonable. So we expanded them to 5 milliliters with dead H2O. Let me get it right. So, too many combinations here. And so we did that, and then we proceeded to take 1 milliliters of each of the samples and count it raw. And then we went ahead while this was going on and took 2 milliliters of each of the samples and vacuum distilled them in an apparatus that was constructed that very day, and counting first the weakest samples and proceeding with the highest activity sample as the last one. This we proceeded to do, and then as the samples were ready, we took 1 milliliter of each of the distillate and counted it in the counter, each time getting a beta spectrum of the results along with the gross counts. That was all done on Friday. Unfortunately, we're not able to count them for any long period of time over the weekend because priority samples that had to be counted, and so we did not have the facility of the counter. We proceeded yesterday to take some of the remaining water and count 2 milliliters of each of the samples that was remaining that had not been put in a cocktail, and put them in a different cocktail and counted those yesterday for longer periods of time along with the original samples that were counted Friday. So we counted all 3 sets again yesterday. The numbers are still being analyzed, and I wasn't prepared to give you a presentation today, otherwise I would have notified my wife to make sure that VCR was hooked up, and as it turns out, she's out walking, but she's going to miss all this. Anyway, the results are what you're interested in, and let me proceed with that. I might say that the results were consistent among the 3 different types of counting that we did. The raw in one type of cocktail, which was Optiflora, which is a packet cocktail. The second one, which was the distillate, which was counted also in the same cocktail. The third one was counted with a Instagel, that was the 2 milliliter samples. Anyway, they were consistent among themselves. The first one, the D2O, we counted that and got a value of approximately in I want to emphasize this is very preliminary, so it's very approximately 100 disintegrations per minute per milliliter, compared to about 180, which was a value given to us by Texas A&M. That's the D2O. The D2O plus LIOD, we got about the same value, which we expected, 100 D per M per milliliter, compared to about 240 D per M per milliliter given to us by Texas A&M. The standard, I don't remember the exact value, but our number was about 6% lower than theirs. This could be accounted for along with the some of the discrepancies by the pipetting errors, possibly some losses and so forth in the transferring. The fourth sample was, let's say it's the weak cell sample. That value by Texas A&M was about 1,300 D per M per milliliter. Ours is estimated, and with emphasis on estimated, at about 900 D per M. And the reason I say estimated is because there was some loss of material en route or at Texas A&M. When we eyeballed the sample, we could see that there was less material than in the other sample, which was a hot one, and which looked like about a half milliliter, but the one that was supposed to be a half, the weak one, looked more like around 3/10 to 4/10. Due to self-imposed pressure to get some numbers out, we didn't weigh the samples, which in hindsight we should have, to get a better value of the total amount of material in each of the vials. In any case, with that estimate of about, well, we took an average between my value, my estimate of 3/10 and somebody else's of 4/10, we used 0.35, and it comes out about 900 D per M. The most important one, of course, is the last one, and that one we measured at about 2.0. One value was a little bit less, like 1.9 something or other. 2.0 million D per M per milliliter compared to 2.13 D per M per milliliter given by Texas A&M. That is a most interesting number. It's interesting because it's so high. It's also interesting because we can't think of a reasonable explanation for it other than some nuclear reaction, probably fusion. And so that's the bottom line on that one, and I think Bob wants to say something.
We chose to first neutralize the samples because of the effect of chemiluminescence when you have high levels of OD ion. And then in addition to that, we decided to do a vacuum distillation of a portion of the sample to completely eliminate any solutes, because there were, or we had been told there were minor quantities of other materials. And so to be sure that none of these had any effect on the counting procedure, we did this vacuum distillation, which is a rather trivial apparatus to set up, but it eliminates a lot of uncertainty.
Well, that's it. Thank you very much. And we will take all the questions at the end, I think, instead of taking them one by one, because otherwise we shan't to get through, and we want to be able to make the discussion very fluid and last as long as it needs to. Now, the next one I have down here is how to get large D-PD ratios. Is Dr. Storms ready to talk about that? Yes. Can talk at the microphone here. They're live.
No built. Okay. Thank you. Well, I'd like to describe for you a study that Carol Talcott and I have been making in an effort to achieve a very high deuterium to palladium ratio in the electrode. We believe that if fusion is to occur at all, one needs a very high stoichiometry, near or exceeding unity. And indeed, we were treated to some very excellent and well-done studies this morning that showed that PD 0.8 is probably a lower limit at which fusion does not take place. And if we're going to find fusion, we're going to have to find it in higher stoichiometries. It's a real challenge then to find ways to get to this region. And I'd like to acknowledge some of the contributors. Bob Sherman has provided contact with Dr. Pons and also others in the field. Roland Jalbert has been analyzing our samples for tritium and provides neutron measurements for us. Marianne and Roy David provide technical help. Ron Ellis, Phil Armstrong, and John O'Rourke have provided the single crystals that I'll describe. But like everyone else, when we heard of Pons's and Fleischmann's discovery, we set about creating a very fancy calorimeter. We went to the literature and discovered that in order to get high stoichiometries, we had to put a poison on, so we found some poisons and we put it on some palladium and put it in the calorimeter and sat back and waited, and expecting the neutrons and the heat to roar out, and we'd be very happy. But during that interval, we began to realize that, first of all, we had to have a high stoichiometry, and second of all, we had no way of knowing what that stoichiometry was in our calorimeter. So we shut that down and instead set up a series of cells in which we could determine the stoichiometry by weighing the uptake of deuterium and by monitoring the dimensions of the palladium. We made the palladium by arc melting 100% pure, that's Johnson and Matthey's claim, palladium powder, and then rolled this into a coin about 2 centimeters in diameter and about 2 millimeters thick. And it's those samples that I'll describe. We've now looked at a number of different systems, different so-called poisons. The ones that are starred are the ones that I'll try to talk about. I don't have time to go into all the details. We have looked at a number of sulfided samples of different layer thicknesses, carbon on the surface, zinc, copper, and a palladium rhodium alloy, which I'll describe in some little detail. But first, let's look at the behavior of palladium as you might get it off the shelf, pure on the surface, stressed because it was unannealed but rolled from this button. And this is a typical behavior that we experience, and many others have as well. You'll notice that the content of palladium rose. It tended to level off. We changed the current. It went up again and then leveled off again. The ideal line is that charging rate that you'd expect if all of the hydrogen went into the palladium that was available from the electrolytic reaction. And you see we do not put all of it in. A certain amount goes off as gas. And this leveled off at about a little under 0.8, about 0.78. And nothing seemed to happen for quite some time. We raised the current again. Nothing happened. So we turned the current off, and you can see the slow release of the deuterium as the sample approaches asymptotically the equilibrium value of deuterium in palladium at 1 atmosphere of hydrogen or deuterium at room temperature, which is about 0.67. Now, not shown on this history, over the last couple of days, we raised the charging current quite substantially, and the level did go up above. It went up to about 0.81 or 0.82, and it went up from the position that it occupies there to about 0.82. Oh, the current raised. We went up to a total current of 1.5 amperes. Now, I should point out that these are total currents. The area of the sample is about 6 square centimeters, so divide it by 6. I'll let you do the math. But it was a substantial increase over 400 milliamps. Now, while we're measuring the weight increase, we are also measuring the thickness. And I'll get this up so you can see it. And you'll notice that there is a fairly decent linear relationship between the dimension increase and the deuterium to palladium content. This is reported in the literature. It's known. In fact, there have been similar studies. This would be useful to quantify if you were intending to measure your particular ratio. It's a very simple measurement to make. As far as we can tell, but we've only gone a bit beyond this with other samples, and it does seem to be linear within that range. We haven't gone all the way to 1, I might add, so any of you want to leave now, you may. We can't tell you how to get to 1 yet. Now, here's another typical sample. This one was prepared in exactly the same manner as the first, except that it was heated at 1650 in vacuum for an hour. As a result, it lost a little weight owing to vaporization, but it also got a very good and thorough annealing. When we first started putting deuterium in, nothing happened. It took up just a little bit, and pretty soon exhausted our patience. So we, at this point, reversed the current and to here, and then returned the current back on again, and you'll notice it went up nicely and hit a new plateau. Reversed the current again. It went up still higher, and you'll notice that each time this was done, it went to a still higher value. We don't know at this point why that happens. It could be because we're introducing dislocations, because as the hydrogen is withdrawn, the lattice does not return to its original condition. It might be because we're removing impurities from the surface in that process that were placed on there during the annealing operation. Or it might be we're applying an impurity to the surface from the cell itself. But this is something that happens in more than one experiment. And you'll see another example. And it does create a little caution because if you're very thorough and you do a good job and you anneal your samples, you might very well never be able to take up deuterium. We tried a number of poisons. Sulfur is known for quite a few years to be a good poison. Palladium, I might point out, has been looked at in a number of different ways. Some people like to have a catalytic surface, and other people want a poison surface. The people who want a poison surface are trying to get hydrogen in, and those have generally in the past been people who have been studying superconductivity, because this is a good superconductor at high stoichiometries. And so people have tried sulfur. The material took up hydrogen very nicely, came up to very near 0.8, about 0.78. The current was turned off and it decayed down. We noticed that if it's well poisoned like this, it doesn't decay down quite as rapidly as it would if it were a clean surface. We tried the current reversal technique on it, and okay, thank you. And it never did come back up to where it was. But you'll notice that the thickness also does not come back down the same line. When you do a current reversal, take the hydrogen back out, you have a residual expansion. One alloy that behaved very, very nicely, and we have great hopes for it, is a palladium-rhodium alloy. It came up very smartly, reached about 0.9, one of our best samples. It shows a very nice linear relationship between expansion and the concentration of deuterium. We believe, owing to the fact that this stuff does not show the uneven growth that palladium shows. Palladium will grow humps and bubbles and little things on the surface. It gets sort of irregular, and that throws off the thickness measurements. This does not do that. Beg your pardon? At 10% rhodium. Now, single crystals offer a unique opportunity to study the behavior in an environment that's a little less compromised by dislocations and uncertainties as to how this thing goes together. We had two single crystals, one that was grown with the 100 plane parallel to the axis and the other grown with the 111 plane parallel to the axis. They both behaved exactly the same for 100 hours, taking up very little deuterium, typical of an annealed sample, as they would be. And so in keeping with our current reversal, we did that on this sample and promptly discovered that it came up to almost 0.8. One reversal. The other one now has been reversed and it's coming up, but not as nicely. And this is the last two slides right here. This one shows you the sort of overall view of the expansion. You can see the statistics are fairly good if you don't take into account those that were where the deuterium was extracted out. And when you reverse the current, it takes it all back out. I mean, you can get practically all of it out. You have to wait a long time if you had a lot of it in there. I would like to suggest two commandments of cold fusion research. There'll be another 8 to follow, not from me, but by others, I'm sure. But I would like to suggest that the first commandment is be sure that the deuterium to palladium ratio of the anode or cathode is near or greater than unity. The palladium at least. And the second commandment is make no conclusions in public about the possibility of cold fusion unless the first law is followed.
So I call it the Fleischmann-Pons effect. Now, Dr. Tanihati is the next one we're going to hear. He's talking about ion beam analysis and the hydrogen and deuterium and their competition in palladium.
Thank you for introduction. We submitted two papers in this conference. One is the measurement of neutron, and the other is the ion beam analysis. That is the one I should present here, and I will briefly introduce what the method of analysis. This is very nice technique using the Coulomb scattering using heavy ions. And you can see if you have some content in the sample, you see the Coulomb scattering. If Coulomb scattering happens on the surface, you see certain energy in the scattered particle. Thank you. And then depending on the depth, how much they are in, you have this width of the spectra, you see. So you can see how much contents are involved by this height and also how deep they are in. And if you have other elements or other particles, because their mass is different, then they start up from different energies. So you can separate other particles. And what we did is originally we tried to do this to see the possibility of the tritium or helium-3 or alphas. But after the electrolysis, we found very funny things, curious things. One is that this is the one without any electrolysis. It's so-called clean palladium. Then you see at the surface a lot of concentration of hydrogen. So you keep the palladium in the air, there's the water or such things. So you get the hydrogen on the surface at the very beginning. Then if you put this one on the electrolyte, and after electrolysis of 9.5 hours, for example, this is for light water condition, you see the concentration of the hydrogen inside the palladium. And then the thing is, even if you do the same thing for deuterated lithium OD in heavy water, by some reason that hydrogen got into the palladium much faster than deuterium, so that you see a lot of contents of hydrogen, but very small amount of deuteron in there. And also, in this case, that you see a lot of lithium in there. And to see more about the ratio of the hydrogen and deuterium, that we did two-dimensional measurement, but this axis is energy, it's the same axis, but we also measure the time of flight, so that we measure the velocity of the particle. If you know the energy and velocity, you know the mass of those things. So we select this part. Those are the proton and deuteron. Then amazingly, after 9 hours of electrolysis, you got only very small amount of deuteron inside the palladium. So if you keep, even you clean the palladium, but if you keep it in the air, that you get the hydrogen on the surface, then this hydrogen goes into palladium site much faster than the deuterium. So you never get the deuterium inside the palladium. So this is more of the warning for the measurement, especially for a physicist who doesn't know those things. I'm a nuclear physicist, and I was really surprised with this. And this is other type of the electrolyte. This is Jones used. In this case, it's amazing that there's no sign of deuterium inside the palladium after 9 hours of electrolysis. Only hydrogen goes in, and even hydrogen seems like diffusing very slowly in there. That's why you see this exponential type of shape with depth dependence. And so, and what we did is that the very simple thing that if you are using some accelerator, you know about the palladium leak for hydrogen ion source. And we tried the same way, that we heated up the palladium in the vacuum and up to 450 degrees. Then put the deuteron gas in there, not the air or neither nitrogen. And then put that directly into D2O. So you never put palladium in the air or other environment after pulling down hydrogen. Then we got very nice spectrum of deuteron diffused into palladium, and from the same scattering data, this is same scattering data, we know that the ratio of the deuterium and palladium is very close to 1 to 0.8. So one thing is you should be careful that keep the palladium out of water or something, and one method of putting a lot of deuterium, this is still 0.8, so it's not enough to make more than one, but anyway, you can make some sort of things here. And what's the ratio you have? I would say 0.8 plus minus 0.1. Okay, and we just give one figure that I'm a nuclear physicist, and I think I can do as good measurement of neutron as some other person do, and we use two very high efficiency liquid scintillators for discriminating gamma rays and neutrons. And we use two detectors because if there is some neutron emissions, two detectors should behave in the same way. And after like 20 hours or so of the accumulation, I think we see no sign of the emission of neutron. Even we use the good sample. I believe that a good sample starting from 0.8 of contents of deuterium.
What was the Y scale?
Y scale is the count, and count is written in here. It's a subtracted count.
So 128 counts per what?
It's like 20 hours. And then after this, if I do the same type of calculation what Jones did, our upper limit is like 9 times 10 to the minus 25. But I'm not sure about this. This is really a volume effect or just a surface effect. And I think from our spectrum that we think the 10 micron would be, we know about the 10 micron. Then if I put that number, then upper limit is 10 to the minus 22. Thank you very much.
Thank you very much, Dr. Tanahati. And now I think we have Dr. Yendel, who's in the audience at the moment and didn't want to come and sit up here as yet anyway, but he's got his microphone. Have you given him a microphone? Dr. Yendel. He's going to talk about transient emission of neutrons.
So I'd like to report on an anomalous neutron signal from deuterated palladium. This experiment was made at the ISCMNS Institute of Physics in Stockholm, and this is part of the Euratom effort to evaluate cold fusion. The group consists of Birger Emmott, senior experimental physicist, Irena Godowski and Václav Godowski, neutron detector experts. Dag Norris is an expert on metal hydrides. I'm a theorist and therefore the most expendable member of a collaboration right now. Okay, so this is a sketch of our experiment. We have an electrolytic cell mounted on the neutron detector. The negative electrode is a palladium bar, 27 grams on this occasion. The positive electrode is a platinum net. We have standard purity D2O plus lithium hydroxide. The cell is designed to have a minimum amount of screening material between the palladium and the detector. So there is less than 1 millimeter of heavy water and a thin Mylar window. And we have turned the cell to place the palladium surface very close to the detector. The detector consists of 57 BF3 counters. Now we have tried to find some cold fusion since the beginning of April with only negative results apart from this event. Where do I put it? Mm-hmm. Okay, so we used a fresh piece of palladium and we pre-treated it by mechanical polishing and by ultrasound. And this is what happened. Zero time is start of electrolysis. For the first 4 hours, the signal was consistent to background. So this is 1,000 second intervals. And our background is about 12 counts per 1,000 seconds. Now after 4 hours, we had an enormous peak, 10 times background. And in each of these two, 1,000-second intervals, we have about 120 counts. Then the signal went away, and we had a second and a third peak. Then it faded, and for the rest of the time, and for another 5 hours not shown, the signal is again consistent with background. We don't have this kind of fluctuation in our backgrounds. We have studied the background for about 3 weeks. This is a sample of background taken before this run. And the average about 12 counts. After the run, now directly after the run, we tried to repeat the successful run, and that was not possible. But we also took a lot of background. This is another sample of background. Again, an average of 12 counts. So presently, we have no explanation for this anomalous signal. The people who are running the detectors are aware of the possibility of vibration, mechanical vibrations, moisture. This data was also taken during a weekend when all accelerators were off. No one was working in neighboring rooms. So we have no explanation for what happened but as a true signal or something strange going on. Our interpretation of this event is that by comparing to calibration with a Californian 252 source, it looks like fast neutrons. Our efficiency is 0.1%, and the angular acceptance angle is 2 pi. So this signal would correspond, the large peak would correspond to 240 neutrons per second. And the volume of this sample is 2.4 cubic centimeters, so we have about 100 neutrons per cubic centimeter a second. In the unlikely event of this being thermal neutrons, we have much higher efficiency. And the signal would then be 0.5 per second. But we had no moderating material, so this would have to be either backscattered thermal neutrons or prompt thermal neutrons. Okay, thank you.
So thank you very much indeed, Dr. Tenney, Dr. Yindel, and I guess that at least we have one positive report. Now the next one, I'm not too sure whether there won't be some kind of contrast, but I understand that Dr. Moshe Guy is going to comment on pulse shape discrimination in neutron analysis. Moshe Guy.
Yeah, I would like to add 2 thou shall not. The first thou shall not. Thou shall not use BF3 counters for neutron detection. I think we have enough of it. It's about time we start doing serious work. And I think what we learned in the last 2 months is that all of the results which were very much questionable came from BF3 counters. And I think we must bring this to an end. We got to do some more professional work. The fourth thou shall not. I would like to make a comment concerning the use of liquid scintillation for pulse shape discrimination, for gamma to neutron rejection. This is only a comment. This is not a talk. I will show a lot of the data that I would allude to in this comment tomorrow in my longer talk, but I would like to bring your attention to how problematic it is to do a good neutron measurement, and in particular to the use of pulse shape for the discrimination of gammas to neutron. I went through this with my own feet. A month ago, I thought I discovered cold fusion, and I had an argument which was 1 week long with my collaborator, from which a different setup has occurred. And there's nothing like the pleasure of winning the same argument twice. I had a long discussion with Kelvin Wolf about it today, and I have also read the paper that was given to me by John Schiffer concerning the Gran Sasso experiment, in which pulse shape discrimination was used. So let me tell you what we thought we found and how we came out of it. In the first day of our experiment, we thought that we can detect neutrons by doing pulse shape discrimination, and we thought, aha, we have a rejection of the order of 500. We measured it with cobalt-60 and cesium, which gives you only gamma rays, and therefore you can see what is the tail. And in this case, we had a very low count rate, which is about 100 counts per hour with a very large efficiency. And lo and behold, we saw a spectrum very much similar to the spectrum that we saw today from Kevin Wolf, with similar characteristic, with similar count rate. It had an edge at 0.9 MeV, electron equivalent, which is very close to the required energy. At 4 o'clock, when my collaborator from Brookhaven left to take the ferry, we made an agreement that we keep our mouth shut about this experiment, and we don't tell anybody about our discovery of cold fusion. When they arrived at home at 9 o'clock, they called me and asked me how does the data look, and I told them I think we have a big trouble. I sat down and started thinking about how can nature fool me, and I think I found out how nature would fool me if I indeed would have announced that I found cold fusion. The conjecture that I made is the following. Again, I will show you the exact data tomorrow in my talk. When you do a pulse shape discrimination, basically the idea is the following. When a gamma ray comes to your liquid scintillator, it liberates an electron with a Compton effect. The electron rattles around in your detector and gives you light. Neutron liberates a proton. The proton does different atomic excitation. There's a metastable state which is associated with an S1/2 state and give you a different timing, a different rise time from the pulse. The same thing can be mimicked if you have a light which is scattered inside your detector and quote unquote is trapped. The light is bouncing around. Given it's not going to happen for every time, but that's why we call this a tail. And what was clear to me is that the fact that I've measured the tail with a source does not mean that I can conclude about my experiment, because it's quite possible that the gamma rays from the source will go to a different location in my detector where the gamma rays from the room are coming to all over the place. So at that point, there were two possibilities, either to go to a Monte Carlo calculation or to do an experiment. So the conjecture was that if the light is trapped in my detector, the gamma will look like a neutron, will have the pulse shape of the neutron. So when I put a gate on my neutron, in fact, I get a lot of gamma rays. Because the light has been now scattering many times in the detectors, there is light absorption and there is pulse height deficiency. So then, for example, if you have potassium-40, for example, if you have a glass cell, if you are anywhere in the room, there's potassium-40, but in particular, or if somebody put a piece of wood to, for example, raise some level, all of these are in material, then the Compton age from a potassium-40 should occur at 1.2 MeV, and that's all what you can see in the liquid scintillator is a Compton edge, basically. Because of what I told you about the pulse height deficiency, the edge would be lowered, and depending upon your exact detector, you might see something which is different. A week later, when we came with a different setup, we in fact found that my conjecture was correct. There is one thing that you cannot fool, and that's the speed of light. Gamma rays are moving between two detectors. Gamma ray would be moving with the speed of light, where if you have a neutron scattering from one detector to the other, they would move at 3% of the speed of light. So the timing between these two, so what I'm trying to say is if I have a Compton event in this detector, I would now detect the leftover gamma rays in a second detector. And if I do that, because of the geometry and the distances and the speed of light, the timing will be slower than a nanosecond within my time resolution. But the time for successive neutron scattering is of the order of 7 times my time resolution. And in fact, when I look on that, those events were totally removed, and in fact, the background was reduced by a great deal. So my comment is that if you want to do a very good neutron counting, you cannot use just pulse shape. You can really have to do beyond that, and you can really have to work on reduction of your background. Thank you.
So I guess we've come to the end of the experimental aspects of these 10-minute presentations. Now we have 3 brief presentations on the mechanistic side. And the first one is Dr. Kim, who's going to talk about his mechanism for fusion. You've got your microphone.
Okay. I don't have any thou shall not comment rule yet, but I will make up as I go along. There is a manuscript I have written and submitted to physics letter, but I will not make copies available until it's accepted. After it's accepted, I'll probably send you preprint for those who request it. But the basic idea I like to propose is this cold fusion process, where you start off with thermal neutron. In this Fleischmann-Pons case, this could be background thermal neutron. If you're doing slightly different experiment, this might come from different neutron source. But this reaction has enormously large cross-section. I think it's the second largest neutron capture cross-section besides cadmium, which has about 20,000 bonds. Now, prismarily, tritium is created at the 2.73 MeV in a heavy water, but since it's a charged particle, it loses energy very quickly, in order of nanoseconds. So it doesn't have a large probability of interacting with the deuterium to proceed to second stage, which is this one. So the crucial point is avoid ionization energy loss. And by accident, Fleischmann-Pons may have accomplished it. I can design experiment in which ionization energy loss can be avoided. Now, of course, going through this process, and if you make 14 MeV neutron go out of system, then that's the end of story. You can't really gain sufficient amount of heat. But somehow, if you can recycle this 14 MeV via many different processes, including palladium, which I'll talk about later, and feed back into equation number 1, then there is a chance that one can have a chain reaction, and if the generation factor is greater than 1, then one can make it become critical. And once critical situation occurs, it doesn't matter what kind of flux you had to begin with. TD cross-section. If you multiply cross-section times the velocity of tritium, you can, from experimental data, you can make this kind of plot. And if tritium is created about 2.7, which is about here, and if it stays, if energy loss is very slow and stays within this window up to here, then it can go. But if tritium is degraded so quick and goes through this window so quick, then of course the chain reaction will occur, as in the heavy water. And let me remind you that this is a tremendous temperature if you are trying to translate in the tokamak. For instance, tokamak is trying to create this kind of temperature right here. Now, if you make a very elementary calculation with background thermal neutron, then you can show that if it's subcritical, nothing will happen. You won't see anything. Heat is too low, and many other things are too low. So crucial point is, can one reach critical stage? And let me show you what kind of situation we'll be in if you have a constant neutron source, in this case a thermal neutron. Then you will essentially reach this level and you stay on, which is extremely low, so that no one will see it. But at some stage, if you reach k equal 1 or k greater than 1, this line can take off like this or like that. Then you can generate lots of heat. And of course, whether one can sustain the chain reaction all depend upon how you keep a neutron economy. Remember, in a fission reactor, you usually produce 2.4 neutron within the one cycle. Now, in this case, you only have a 1 14 neutron, and it's very hard to really do it. And some of the things it might help, I listed some of those. I couldn't look up some of cross-section yet. And then some idea about adding beryllium. For instance, if you add the beryllium in heavy water, because of this large cross-section, this will win out neutron deficit so that it can help. So we don't know whether this can be accomplished in Fleischmann-Pons experiment. I can design a device in which hopefully one can make a self-sustaining reaction go with the external neutron source. So my plausible explanation of heat excess generation of Fleischmann-Pons is perhaps they reach the self-sustaining stage so that you create lots of heat. Some of the reason why that might happen could be that all the things he had around it may acted as a moderator or refractor of the neutron. And the palladium may have acted like a neutron moderator or refractor. And of course, amount of tritium and neutron present at given time at the critical stage will not be as large as you would expect because they are being recycled. Now, one scenario of whether this stage reached in Fleischmann-Pons experiment is if I look at there are electrodes, you have very high concentration of ions right on the surface of palladium and then maybe within certain distance. And if the tritium doesn't lose energy through the ionization on that region, then TD fusion can take place with the highest possible cross-section, even above the aim of the tokamak. And once the neutron is generated, those reactions might provide excess neutron. This is needed to sustain the reaction. Now, for instance, if you look at 14 MeV hitting on the palladium, some of the palladium absorbs the neutron, so you lose, but some of them create a 2 neutron. I looked up some cross-section, which is reasonably large amount. So the palladium may have acted as not only as a moderator, but refractor producing maybe excess neutron. You don't need to really produce at each stage. You don't really need to, well, the K, factor K, need not to be very large. It's, you know, in a fission reaction, it's a 1.007 is doing it. That's what we need. 2 minutes? And of course, the rate will be helped by having very high concentration of tritium near the palladium instead of tritium spread out many different places in different places. Now, so I like to test this hypothesis. I like to suggest some of the tests one can make. One possibility is to really use external neutron source instead of try to depend on background thermal neutron. And then, of course, the clear signal of this chain reaction would be detection of 14 MeV neutron. And, of course, another product would be helium-4, which should be more abundant in the heavy water than the palladium than tritium. In addition to heat measurements, some people have been doing. In addition to that, I suggest, yeah, last one. I suggest those things. This could be Dow, this will be Dow shall not, but this will be Dow shall. Last picture is just schematic diagram of having a neutron external source with neutron moderator refractor wrapped around. Thank you.
Well, now we know what to do. Now Dr. Bush is going to give a presentation. He says he can explain everything, and he's going to use some added help from a colleague, Dr. Eagleton. So we have still 10 minutes for the both of them.
Okay, well, here's the title of the poster that we have up in 3A, and I'm not going to read the poster to you, but what I am going to do is I'm going to suggest some theoretical themes, or at least one strong theoretical theme that I think needs to be emphasized. It hasn't been emphasized and may go a long ways towards explaining things. Is this microphone working, by the way? Yeah. Okay. Seems like I'm talking in a shower or something. Now, just to give us credibility for our theoretical work, I'd like to point out that Cal Poly has no football team, as you see down there. What we claim is that if cold nuclear fusion exists, it probably exists in connection with what we call a symmetry force. And for those who don't like forces other than the four standard forces of textbooks, you might want to just substitute the word wave function every time I say symmetry force. Let me give you an example of this. When we, most of you are familiar with the so-called Lennard-Jones potential energy. And in this you recall that there's the London term, the induced dipole-dipole term. But this first term associated with a repulsive energy here is due to the overlap of the atomic wave functions of the two atoms. And that can be traced, of course, directly to the exclusion principle. Now, even though the exclusion principle is associated with the wave function for fermions, I can associate a symmetry force for that, as this force right down here. Okay, so I can associate a symmetry force that accounts for the exclusion principle aspect of the Lennard-Jones potential. Okay. Now something from Feynman's lectures. Feynman points out that if you have a boson already present, what is the chance that another boson will enter a state where they're already n present? And the answer that he gives is that you get n plus 1 times the probability. It's n plus 1 times stronger than if there were none before. Okay, and let's look at that in a little more detail here. First, with the antisymmetric form of the symmetry force for fermions in connection with an example of two identical particles in a well or box. Okay, so here is the antisymmetric wave function. You're familiar, of course, with trying to put them in the same quantum state. If I let n equal m, what would happen, of course, is the wave function disappears. This is the well-known Paul exclusion principle. On the other hand, even if n is not equal to m, there's an anti-clumping property, because if we try to superimpose these two identical fermions, again, the wave function vanishes. And this is an anti-clumping property. Let's look now at what happens with bosons. Okay, if we look at what happens with bosons, you recognize the wave function. If I now let n equal m, if I had a lot of these, you would say that we have a Bose-Einstein condensation. In fact, in that sense, the Bose-Einstein condensation is just the opposite of the Paul exclusion principle situation. Okay, but here's a case that everybody has forgotten. Okay, what if n is equal to m and I let the locations be the same? In that case, the wave function is also enhanced according to what Feynman has said. And this Dr. Eagleton and I, this clumping property, Dr. Eagleton and I refer to as the inclusion principle. Okay, it isn't the opposite of exclusion principle, because that's sort of the Bose-Einstein condensation. But since this does produce a clumping, we like to call this the inclusion principle. And this has been something that's neglected, has been neglected whenever I've heard conversations about the mechanisms. We think this is tied directly to the mechanism. In fact, we feel that the mechanism that produces the catalyzation of the cold nuclear fusion is associated with a clumping, this clumping mechanism of the bosons, which produces essentially a globule of n degenerate deuterons. The wave function associated with this is then the thing which catalyzes the cold nuclear fusion reaction. And in fact, if we carry this forward, as we've done in our poster session, we invite you to stop by, you find that you get a transmissivity which depends on the number of deuterons in the globule. Here's the expression for the transmissivity. And of course, as that n goes up, because of the exponential dependence, very rapidly the tunneling is enhanced. So to go, for example, from the Steve Jones case of about 10 to the minus 14 watts per cubic centimeter sample to the Pons-Fleischmann case of about 10 watts per cubic centimeter sample requires n only to go from about 12.8, say 13 to 25. Let me just pop this power table on here real quickly. You can see this is the level of the Stephen Jones experiment, about 12.8, which we rounded off to 13. The Pons-Fleischmann level would be 6.2 watts. And of course, everything I'm saying could be just building castles in the sky if it turns out that those globules can't form. So you have to realize that with a semi-empirical model here, we're kind of hedging our bets. But I think this theme should be investigated a little more thoroughly, and we invite your questions, and we invite you to look at the session. What I'm going to do now is turn this over to Dr. Eagleton, who is going to talk about some experimental suggestions for improving the experiment based on this model. To give him experimental credibility, I'd like to point out that he did his graduate work at a school that has an excellent football team. So, you want to? You got it, okay. Read my title.
Okay, thank you. Can you all hear me all right? Okay, let me get over here. Okay, so what we did, we took the theoretical considerations of our model and said, well, how would this change the experimental design of the Pons-Fleischmann type experiment? So that's what I'd like to take you through right now. the principal requirement, according to our model, for this to work is you must have the formation of a sufficiently large globule of deuterons. So now the question would be, what environment should be provided to enhance the formation of such globules? And I've listed 3 such factors, which we all recognize. You have to have these unoccupied lattice sites flush out the H1 isotopes so that deuterons can get in there. Next, they must be, these octahedral lattice sites must be accessible from the surface, which means you have to have a properly prepared surface to let the deuterons get through to the interior sites. And then, that's not enough. The lattice sites must be large enough to allow the formation of a sufficiently large globule. That's why we think palladium is the one that will do it, because it's a unique electron configuration, 4d10 electron configuration. All the others, such as platinum, have the s orbital electrons, which occupy a lot of the space inside the octahedral site, not enough room for a very large concentration of deuterons to get in. So we look at palladium as a logical choice for cold fusion. Now, this is a summary of a sequence of processes and events that will yield or lead to cold nuclear fusion. First, you must prepare the electrode, which means clean the surface, purge the interior of any poisons, unwanted isotopes, and that could involve annealing, of course. The second element is the deposition of deuterium at the surface of the electrode. This, of course, involves the process of electrolysis. But now, once the deuterium is on the surface, it loses its electron to the interior. The electron is stripped off, goes in the conduction band of palladium. This leaves a nucleus, essentially a bare nucleus, on the surface, which diffuses the interior. Now, you must realize that this deuteron does attract a surrounding electron cloud from the conduction band as it diffuses through the palladium lattice. So it does maintain charge neutrality by enhancing the localized conduction band electron wave function. Okay, so that would be the chemoabsorption process where you essentially strip the valence electron from the deuterium. The fourth step would be the migration or the diffusion of these deuterons into the interior of the palladium lattice, and this seems to be where the electric field that Dr. Bakros was talking about earlier helps to get them into the interior by providing this extremely large pressure effect. And there's a combination, it looks like to me, of a process of combined quantum mechanical tunneling and classical diffusion. So as the deuterons work their way through the crystal lattice, I believe both processes are going on. And anyone who's looked at the diffusion rates of deuterium or deuterons compared to H1 isotopes and H3 isotopes, that's the order. You have an anomalous diffusion effect. The deuterons have a higher diffusion coefficient than do the H1 isotopes, and H1 isotopes have a greater diffusion coefficient than the tritium isotopes. So what's the anomalous explanation for this, or what's an explanation for this anomalous diffusion process? Well, the people we've talked to think that tunneling is the explanation for this anomalous effect. The fifth step would be the termination of the deuteron flow. So due to concentration gradients or whatever, there's going to be a flow of the deuterons to the interior. If you essentially purge the interior, the octahedral sites are free. Then at the surface there will be a diffusion gradient, a concentration gradient build up. The concentration gradient then is responsible for the flow of the deuterons to the interior to fill up these empty octahedral sites. By the way, the octahedral sites would have a lower energy, would permit the deuterons to be in a lower energy than with the tetrahedral sites because they're a larger volume. Quantum mechanically, a bigger well permits lower ground state energies. Okay, that's all I need there. Okay, once you've got the termination of the flow of these deuterons into the interior of the lattice, you've essentially saturated the octahedral sites. At this point, we believe that the globular growth will take over. The process Dr. Bush talked about, the symmetry force, due to the nature of the bosons, that they can start aggregating, and more deuterons you get in an octahedral site, the greater the tendency to pull in others. And now, once you get enough in there, the separation distance is going to be sufficiently small that the probability of nuclear tunneling takes place is going to be relatively large, and that's going to be the seventh step here. Now, that is a formation of a compound nucleus helium-4 with 24 MeV excitation energy. Now, according to our model, this the compound nucleus helium-4 is created in the center of this globule, or near the center, surrounded by the deuteron condensate, which is fairly close. Well, what does this imply? Well, excited helium-4 compound nucleus can couple to the surrounding deuterons, transfer its energies to those, or like an internal conversion electron process in atomic physics or nuclear physics. So we believe that this can account for the stability, the high branching ratio for helium-4 by the transfer of its excitation energy to the surrounding deuterons in the globule, which in turn transfers it to the palladium lattice, melts it down in effect, because it takes only about 4 electron volts or thereabout to take a palladium lattice or break all the bonds of a palladium atom. That means divide 4 electron volts into 24 MeV, what you get is 6 million palladium atoms that are going to melt down. So in a distance about 80 to 90 lattice sites away, that area is going to melt down, okay? So that, we feel, is going to prevent any neutrons from coming out as high-energy neutrons, okay? Trying to pass through that meltdown down region, okay? And, well, that's basically it. Thank you.
Well, now we come to the last one, not the least one. And this is Dr. Morgan from Harvard, who's going to talk about a mechanism for calculating cold fusion, Fleischmann-Pons effect.
I'll be discussing work that has been done in collaboration with Henk Monkhorst at the University of Florida on a simple yet accurate model potential for calculating cold fusion rates. The work I'll be describing has been done within the approximation that the fusion rate can be written as the product of a nuclear factor times a molecular factor. I was a little bit disturbed when I first saw Jerry Hale's abstract about how this was in fact not really what was going on, but then I was relieved to hear that although it's not really by any means an exact sort of result, it does seem to work pretty well in practical situations. And what I've written here involves essentially just the WKB approximation, where you can, the primary contribution to the molecular factor involves the Coulomb barrier penetration, which is the integral of essentially something that looks like the WKB factor but modified for the Langer correction, and you integrate this between the limit where the nuclear force cuts in and the upper limit, which is the inner zero of the radical, which is only very slightly different from the classical inner turning point in the WKB approximation. The M is the mass of the reduced mass of the nucleon pair. And what we would like to do is we'd like to find a simple way of estimating the fusion rate within a factor of 10. The reason for this is obvious. When under ordinary conditions, fusion rates are astronomically small, something like 10 to the minus 64 per second for ordinary D2 in the ground state, and you'd like to try to find a way of explaining how on Earth it could be something like at least a factor of 10 to the 40 larger, as implied in the experiment by Stephen Jones. Now, there are extremely accurate calculations I want to mention that have been done on various hydrogen isotopes of the hydrogen molecule. These were done almost immediately after the announcement of the Jones result by Jan Rafalski's group. There also was a nice calculation done by Steve Koonin and Mike Nauenberg. There's also another calculation that was done by Krzysztof Szalewicz and myself and Monkhorst, and that's being reported in a poster session. I want to say also that the motivation for our analysis was an article by Van Sicklen and Jones in trying to make a simple estimate of the fusion rate in D2. Well, as has been mentioned several times already, fusion out of high vibrational excited states is far more important than fusion out of the ground state. This is because the classical inner turning point is so much smaller for fusion out of high excited states. So what we'd like to do, we know that the high excited states are going to dominate the process. We'd like to be able to find a simple way of computing them. The first thing you might try is just saying that your potential of interaction between the two nuclei is just the Coulomb potential 1 over r plus a constant. If you do that, you can do this integral in closed form, and you just get the following very simple result. Again, m is the reduced mass of the nucleon pair, r sub I is the inner turning point. This unfortunately leads to an overestimate of the lambda integral and thus an underestimate of the fusion rate because it neglects the variation of the electronic contribution to the internuclear energy with R. Let me flash up here a graph of the electronic contribution to the interatomic potential energy curve of H2 versus the internuclear separation. These points are taken from a very accurate calculation by Shulevich, Kolos, and Monkhorst, where the uncertainty is enormously smaller than the dots. And as you can see, it's very nearly linear all the way in from the equilibrium separation. So it will not be a bad approximation at all to just replace this with a linear function. So what we do is we write the actual V of R minus E as our zeroth order approximation, which was 1 over R plus a constant, plus a correction term, and we just treat that perturbatively by just doing the WKB analog of first order perturbation theory. Just take the radical and expand it through first order. You get another integral that you can do easily in closed form if the difference is linear, as we've seen that it is. And if you do that, you find that your original formula is modified by simply an additional term, which is actually rather small, which in a relative sense, which accounts for the variation of the electronic energy with the internuclear separation. And this is remarkably accurate, I should say. For the highest excited state of D2, it predicts that the actual number from the calculation by Shulevich et al. Is 145.06, and what we get with just simple analytical calculation is 146.9. So when you exponentiate this, you'd get a fusion rate that was only off by a factor of 10, which would be certainly quite adequate for most purposes when you're trying to account for an effect of the order of 10 to the 40. So let me just again review why this works so well. It works so well because the electronic energy is nearly linear, and the first order expansion of the radical is adequate away from the equilibrium point. It would break down seriously near the equilibrium point. In that case, you'd want to try to do some matching with some sort of harmonic approximation to the potential energy near the equilibrium point. Let me mention a pair of applications of this. First of all, given a measured fusion rate, you can then make a rough estimate of the barrier penetration factor, and from that estimate the inner turning point at which the fusion process is occurring. And so, for example, if we take the Fleischmann-Pons estimate from the neutrons, which I guess has been kind of discredited in some ways by now, that would correspond within a very broad range to an classical inner turning point of somewhere between, say, 0.15 AUs and 0.25 AUs, to be generous with the error bars, which is, again, about 1/5 of an atomic unit, which is a number that others have come up with. But I think a nice feature of this analysis is that it's almost completely independent of the behavior of the potential energy in the classically allowed region, which you don't know very well in a crystal, of course. It just comes straight out from the fusion rate. The other point is that since almost all the action is in this exponential factor, given a measured fusion rate for one reaction involving hydrogen isotopes, you can then estimate the fusion rate for another reaction by just taking ratios and assuming that what's happening in the pre-exponential is a minor contribution. And so, for example, we did this back in April when occurred to us that there is an aneutronic fusion reaction which might account for some heat. P plus D goes to helium-3 plus a gamma. However, when you work out what the ratio of fusion rates are, and assume it's the same mechanism that would be responsible for, say, this reaction and the D plus D reactions, you find that, unfortunately, these fusion rates would be comparable. They would certainly, again, within an order of magnitude or so, but certainly the PD reaction would not be going faster by a factor of 10 to the 7 to 10 to the 10. Now, since it's late, I would like to throw out a wild idea, which I'll do that. Good. That's all it'll take. Namely, there's a somewhat off-the-wall letter to the editor by Grzyński in Nature, in the 27 April issue, which, I mean, I think it's a very nice idea, very nice observation, which is that classically fusion could occur all the time, right? Namely, if you just put an electron midway between two particles of charge +1, like two deuterons, you'd have a net attractive force, and the system would just collapse down to a point, and then you'd have fusion occurring. So this is it's an interesting concept, right? Because certainly I thought at first, and I think many others have thought, that if you want to get two deuterons right on top of each other at some nuclear distance, you can only do so by tunneling. In fact, this is not true. There are classical paths which will allow you to get two deuterons close to each other. And these cannot really be described within the adiabatic approximation. So there's an important question. Could these kinds of classical paths become important if adiabatic tunneling is extremely improbable, as it certainly is with, say, electrons, as compared with, say, heavy particles like muons binding the nuclei together? I emphasize this is a difficult question to answer. I don't know of a good way to get a handle on this other than to do a very complicated variational calculation. I'd like to issue a caveat. This is a mechanism that I believe also occurred to Richard Garwin, as I was informed by Steve Koonin. I'd like to issue a caveat, which is that for dt mu, right, the deuteron triton muon system, there have been extremely accurate variational calculations by Shulevich, Monkhorst et al., and those show that the adiabatic and non-adiabatic fusion rates are only 20% different, and furthermore, the adiabatic rate is actually slightly higher rather than larger than the full three-body calculation.
Well, now the time has come. The time has come. It's open season now, and everybody shall have his chance. The idea now is to concentrate on the people who've spoken in the last hour and 10 minutes, and after that to go to other things, and perhaps the people who spoke the rest of the day. But I would like you to concentrate your questions on the people who are sitting up here. Dr. Yendel, I believe, is sitting over there. And let's ask for some questions. You at the back there, the yellow shirt. Got a microphone, someone? There it comes. Okay, there's a microphone coming. Hey. Oh, I see.
I'm R.T. Perry. I'm from Los Alamos. I have a comment to make about the, I believe it was Kim's paper. A number of years ago, a colleague and I from Texas A&M with a Professor Parrish at the Department of Nuclear Engineering did some experiments in which we took a plate of lithium deuteride, put it next to a reactor to produce 14 MeV neutrons. You will get about 10 to the minus 6 fusions per incident neutron. That's both calculational and theoretical. The second, I have a question, is when the experiment at Los Alamos to measure the tritium, did you have a control? Was there a control of deuterium oxide before a control of deuterium oxide that was not in a cell looked at for tritium?
I think that's your question. Dr. Kim. Isn't that Dr. Kim? Didn't you ask that? To whom was your question addressed?
It was to the first person. The comment was to Lee's paper. It's going to be.
Can you give us the name of the speaker you're talking to?
I believe it was Lee. Kim.
Dr. Kim.
Me. Yes. You will get. The comment is simply you will get about 10 to the 6 fusions per incident neutron in a plate of lithium deuteride. I can't expect that you would get more in a bottle.
Well, all of my equation I wrote down has cross-section, but has a measured cross-section, and the question is, how well can you fully realize a cross-section?
Oh, the cross-sections are well known.
Right. So differing for each different situation, whether tritium is in the material or other thing, like in plasma, you get a different answer.
No, this is I'm talking about a plate of lithium deuteride where you produce a tritium atom from an N lithium alpha T reaction. You get the tritium produced. It slows down in the lithium deuteride. You will only produce about 10 to the minus 6 fusions per instant
Yes,
neutron.
I agree with you. You have to create a plasma where the energy loss due to ionization is essentially eliminated. I agree with your statement.
I think that we better get on. If you could perhaps continue the question at another time. Yes. Yes. You. Have you got a microphone?
First, I would like to make a comment to the gentleman who spoke about barrier penetration from Harvard. I'm sorry I didn't catch your name.
Dr. Morgan.
Dr. Moore. Dr. Moore, you spoke about the Langer trick in calculations of barrier penetration. The Langer trick seems to be an old idea that has been in the literature, and it has been in Landau and Licht's book on quantum mechanics and used extensively. And I would like to comment that when Steve Koonin and myself did our calculations, we did an exact numerical calculation, and we found, among other things, some very large discrepancies, which I would like to comment to you about in the literature, including an earlier calculation of Zeldovich and Gernstein, who in 1960 sort of wrote a review article about cold fusion. Now let me tell you categorically that we found out numerically that the Langer trick, which has been used so extensively, is just considerably off by a large numbers of orders of magnitude from an exact numerical calculation.
May I ask you not to make a speech, sir? Your question is,
now the point
which
is
equation is wrong? Is that right? You're saying that a particular equation used by Dr. Morgan is incorrect.
It's been universally used, and it's just quite wrong.
Right. Well, now let's hear what he has to say.
I certainly can respond to this because we have a preprint
let me
out.
just finish my comment. I haven't finished. I tell you, it's not only wrong. The argument is, you see, that it somehow has the correct analyticity at the origin. So that was sort of the original argument of Langer. I picked up the original paper. The problem is that you can numerically check what the behavior at the origin is, and the power law, for example, in terms of the effective mass or the scale, which would be linear if you took the Langer approximation, turns out to be the 6th power rather than a linear power dependence.
Thank you very much. Your answer?
Well, this is far too complex to address in 2 minutes, but I can say that in the calculations with Shalevich and Moncourse, where we performed both highly accurate numerical calculations, which agreed very well with the calculations I believe you did with Koonin. We did those fully numerically. We also used WKB, and for the ground state of D2, the difference between doing it with WKB with Langer and with the full integration of the Schrödinger equation, there's like a 10% difference at most for the ground state.
The published calculation...
I can't have you anymore, sir.
Well, there's a terrible error here.
Would you mind
the calculation of Langer...
Would you mind continuing this discussion afterwards? May I say in general to everybody in view of this person that it's not possible to have discussions during this session. We just want to have questions, and the discussions can't last more than 2 or 3 minutes. You? Yes? No, you?
I was quite taken with Dr. Storm. Steve Koonin from Caltech. I was quite taken with Dr. Storm's 2 commandments, and I would like to ask whether Dr. Jandel feels that he has violated those commandments. And I'd also ask the same question of Dr. Appleby and Dr. Wolf this morning.
Do you want to answer this, Dr. Jandel? Dr. Wolf?
Sure, I'll answer.
Yes, Dr. Wolf then.
Well, obviously we have been using a BFG detector, but...
That was number 3.
Number 1 and 2. One was that you should have the hydrogen to palladium at least 0.8, or it's back up close to 1. And the second was that you shouldn't make any comment in public until you would obey that commandment. So what is your hydrogen to palladium?
You know this.
The hydrogen, light hydrogen, deuterium, according to our surface analysis, is this 0.5 at the surface. But this was measured about 12 hours after the electrolysis. Then 10 micrometers inside the sample, we have about 40%.
Dr. Wolf, do you want to say anything about this? No, about the question that was asked. Are you disobeying any rules or regulations or... Well, you ask him a question, then you can comment on it.
Yeah, but releasing the news, I mean, we don't have any explanations. We are seeing an anomalous signals. We don't think presently that we have a systematic error to explain this.
Dr. Wolf?
May I address
You may ask a question. You may not start making an address.
The commandment question, the third commandment, the first commandment on deuterium. I think Dr. Appleby or Ceresi will have to answer that one on what they think their ratio really is.
Well, actually, we did not make any measurement of the deuterium to palladium ratio, but we measured the potential of the electrode versus a reversible electrode, and I would say it corresponded to roughly about 0.7 or something like that.
open circuit or with current?
Open circuit.
Open circuit interrupted relative to a reference, 0.7 stable?
Well, I would say it was the short-term measurement. Soon after we turned off the current, we measured the potential. Really.
In fact, if you watch it and weigh it, it varies very little over 5 minutes.
Yeah.
Now, who is next? Yes. You. Go ahead.
I'm sorry.
Question for name is Carlos Melendres, Argonne National Laboratory. Question for Dr. Yandel. How many experiments show those high neutron counts? How reproducible are they?
Oh, not reproducible at all.
Just one experiment.
They also tried to switch off the current for 8 hours, switch it on again, nothing happened. When we took out the sample, cleaned the surface, put it in, electrolyzed for 18 hours, nothing happened. When we got another new palladium sample from the same source, tried again, nothing happened. So we don't have a repetition.
Thank you.
Yes, Professor Bard.
I think one of the most striking things we heard this morning concerns the tritium measurement. And the question is to Dr. Sherman, I guess, and also to you, though, was there a blank done with the palladium cathode, nickel anode with H2O?
No. Well, you've just had one. Yes?
Yes, Dale Darling from Lawrence Livermore Lab, and I have a question for Dr. Sherman. Also, on the analysis that was done, you gave on the sample or from cell B. The question I have, is there a way of backing up from the tritium level that was measured in the solution to what would have been present in the palladium? Do we know enough of the history?
No. I can answer that better than he can.
Okay.
No, there were no measurements made of the tritium in the electrode.
But I guess the question is, how long did the sample sit?
Did it?
In the solution after the cell was turned off, how much diffusion would you expect back into the...
No, we didn't examine that.
Didn't examine it.
Yes?
Nate Lewis, Caltech. I have a comment and a question for Dr. Storms. The comment is that it's well known to people who try to make palladium reference electrodes that in fact you need often to anodize surfaces in order to remove catalytic impurities. The palladium will dissolve For people that are interested in this, there's a book for people that don't know much about electrochemistry. It's called Experimental Electrochemistry for Chemists, and it's by Sawyer and Roberts. And it describes all of the activation procedures necessary to allow palladium to sorb deuterium on charging, hydrogen actually, for reference electrodes. So I think it's a common phenomenon that some anodized samples have to be, some activated samples have to be anodized first to make them sorb deuterium. My comment is, you mentioned that you had actually looked at arc melted palladium to charge them. Have the people at Los Alamos made measurements on calorimetry and neutron detection for that particular type of palladium?
We have not yet done that on the palladium that we use for these studies. We're waiting until we get to a higher stoichiometry before we really waste our time in that.
Yeah. And one more comment actually on that. It's not clear that putting a poison in will actually allow you to go higher in stoichiometry at a given current density, because the current density and potential are related. The poison would affect the rate at which you go to that equilibrium, but shouldn't affect the equilibrium once you're there. If you ever got higher than that via some other method, either putting it into the gas phase or going to a different potential, you could then in principle freeze it in that state by poisoning it. But it's not clear that holding it at a given current density and poisoning it will allow you to maintain a higher pressure or equivalence than you would otherwise get at the same potential.
I'd like to make an electrochemical comment on that. That is true enough. The relationship between permeation, theta, the occupancy on the surface, and the poison is quite complicated. And most of the work that's known about this for iron, and what I'm going to say is about hydrogen on iron and not deuterium on palladium, but I suspect they're rather related. Whether you increase the rate of going in and the final rate inside is very much a balance, because what you do is you affect the equilibrium constant between the inside and the outside, but at the same time you affect the kinetics of the reaction on the surface. But what you may probably do with many poisons is to increase the overpotential rather than the H inside. And because of those mysterious equations that I briefly presented right at the beginning, that may have very profound effects. Yes?
This is a question to Dr. Storm, I think it is, but it's actually only a disguise, because it really is addressed to everyone. And that is, why on earth are people concentrating on the palladium hydrogen system if what you want is simple experiments with high deuterium to metal ratio? There are many other metal deuterium systems which are accessible at much higher ratios of deuterium to the metal, and for which you can get the deuterium in from a gas phase equilibrium, so you don't have to worry about all this electrochemistry mishmash and complexity. You could do your calorimetry. It's really a bit of a puzzle, as someone who's worked on metal hydrides for many years, why this focus on the palladium? Is there something about the palladium that you think is affecting the fusion reaction, or is it just the concentration of deuterium?
Well, if I may have a go at it, you addressed it to Dr. Storm and he can reply, but I would just like to say I think it's just a human reaction to the fact that these claims were made by Fleischmann and Pons. Most of us, of those of I know, the many teams I know in the States, all have titanium, titanium iron, and various other metals in the cupboard, and some of them on the bench, and some of them being charged up at this time. So we are working at different things. We will realize that the obvious ideal and wonder would be titanium, which of course is about 1/300th the cost of palladium. So we're all doing that, but there is a possible reason why palladium might be unique. You see, those other metals which have so much splendid concentrations of hydrogen, as I well know from my studies on the storage of hydrogen, some of them have as much as 2 and 3 atoms per hydrogen atoms per atom metal, they have a quite different type of hydrogen. The great thing about the hydrogen in palladium is it's extremely ionic, it's extremely protonic. And that seems conceptually and perhaps rather intuitively to be rather favorable for the concept of fusion, rather than a great big gangling H, which has a tremendous radius and it's 0.7 or something like that. So it may well be that if this whole phenomenon occurs at all, and if there is fusion occurring there, it's possible it is occurring in palladium. But we are doing a lot of other work.
May I add to that?
Sure.
Palladium also has a unique character to it, or at least potentially does. in that the two deuteriums can occupy the same lattice site and therefore be very close to one another in that lattice, whereas most of the other crystal structures are further apart. In this particular case, there's a high probability that you can in fact make PDH2 if you put on a high enough activity. Well, I base it on two things. One is that there is an analogy that can be made to the thorium-carbon system. That system, thorium is a face-centered cubic element. It takes up carbon in the same manner as palladium takes up hydrogen. And it goes to THC2, where two carbon atoms occupy the same lattice site. And so you can put two carbon atoms in, which are quite a bit larger than hydrogen. It makes it somewhat probable that you might be able to do the same thing with hydrogen.
Before I go any further, I would like to say it's now 9:30, and I want to know if by a show of hands, how many people want to discuss with these lads here, or shall we chuck them out and get another lot up? Please raise your hand if you think you have a question for these people here. 2, 3, 4, 5, 6. Well, suppose I take 3 more. Okay, you. No, you. No, the green shirt. Yes, the one near here.
It's Flemming Wiesenbacher. Well, we heard again now, and we had also a comment to this Booth-Eagleton mechanism there, and really reminds me about Alice in Wonderland. I mean, this field of hydrogen metals has been studied for more than a century now. There's textbooks about it, and everyone in that field knows that that thing cannot happen. Two hydrogen cannot sit at an octahedral site in a palladium hydride. It's known experimentally and it's known theoretically. There's several papers showing, and I'm standing with one here, that if you have a hydrogen molecule in a metal, it's more repulsive in a metal than it is in a vacuum. So, I mean, why inventing all these funny things if you know it's not happening? I mean, palladium is no different than titanium and any other things. Hydrogen repel each other in a metal system. It's well known. Neutron diffraction studying, channeling studies knows this. I mean, we've known it for a long time.
Well, despite the fact, sir, that we want to get the heat, I think we want to have more light than that heat. Anybody over here? Yes. Oh, the one at the back. Yes, you. Yes.
Chuck Scott from Oak Ridge. I addressed this to Dr. Sherman. You had mentioned that the samples that you got in which you measured tritium had not only D2O and LiOD, but some other things, presumably poisons and so forth. I assume that you know what they are, or perhaps the Texas A&M folks know what they are?
It wouldn't be appropriate for me to comment on the constitution of the Texas A&M solution.
Well, I can certainly tell you some horrible things that are in them. In these solutions, there are certainly traces. I'm referring to these particular solutions, and I'm not referring to Texas A&M solutions in general, but we have found that there are certain amounts of iron, some have chromium, and some have silicate species in them. And for this reason, we've changed the vessels in which we do the charging for weeks to be Teflon vessels, because it obviously comes from glass dissolution. The traces of iron probably come from a heater in one of the cells. The chromium comes from a thermometer or something like that. These are, of course, parts per million, but they're definitely there, and you can see them. Various types of analysis. Just a moment, just a moment. Yes, you. This is the last question of this lot.
I'm Su Huanwei from Surrey. My question is to Dr. Morrow. The electronic energy used in your calculation, is that for hydrogen in free space or the hydrogen potential inside palladium?
Okay. The one I illustrated is for the hydrogen molecule in free space.
But it is well known also in my calculation, which is in the post session. The hydrogen potential inside the palladium is very different from hydrogen potential in the free space. Therefore, we think realistic calculation must use realistic potential inside palladium.
I absolutely agree. I have derived a general formula where you can plug in any potential you like as long as the electronic contribution is approximately linear. for reasonably small r?
From our calculation, we find it's not linear in palladium.
The purely electronic contribution after 1 over r has been subtracted out?
Yes.
Okay, I'd like to learn more about
Because you have to
that.
consider all the symmetry situation inside palladium, which is different from free space.
Thank you. Thank you very much. Right, thank you very much, gentlemen. Thank you. Now, don't all go, no. Unless you want to. There are a number of people slipping away, and it is 9:30. But for those who want to stay, there'll be more discussion. It's up to you. The instructions I have is that this session is open-ended, and if you want to stay, do some more, we will stay. Now, when we're down to about half of what we have at the moment, maybe we'll think of closing. This is now general questions on anything that we discussed this morning. You over there. Now, mind you, these are questions.
Well, it's a question, but an illustration of the
Illustration of a
question.
It's not 1 minute lectures.
It has to do with Dr. Storm's measurement of hydrogen.
Wasn't that the last lot, Dr. Storm?
Well,
That's
yes.
all ended now. That's all ended.
Well, it's a general point.
general
There's a
point.
way to measure deuterium in these materials by impedance techniques, and they're relatively simple. And this slide shows relative resistance change of palladium being charged by hydrogen, and this can be done relatively simply. You don't have to weigh samples. You can take them out and measure their impedance. I'd just like to point out a couple of factors. When the material becomes saturated, if the current is reversed, you can go into what appears to be a supersaturation region, and this could be related to deuterons or deuterium-deuteron equilibrium within the sample changing. There's also been Hall measurements made now of these materials, and I'd like to stimulate people to try to make measurements combining impedance measurements and, say, deuterium concentration by either neutron scattering or Hall measurements.
Thank you. Got another question, Steve Feldberg. Mike, the lady's coming.
Yeah, this question's addressed to Kevin or any of you folks who've been analyzing for the tritium, which is a rather fascinating observation. What would be the effect of H2O2 word in the solution on that analysis?
Kevin, answer that?
No, I don't, quite frankly.
Just checking. Peroxides, hypochlorites, bleaches, as well as hydroxides drive these scintillators crazy. It pumps them up, makes them much more active for chemiluminescence. Of course, it's not an infinite time. It just means you have to leave these things in the dark longer to die out and be aware of the problem. And there have been scares, errors made in health physics in this type of counting where they thought, my God, the world is coming to an end. We're contaminated with tritium. Okay, but you do have to be aware of that. Does that answer your question?
Well, the question, of course, the real question is, did you take precautions to avoid this? It's
Right.
not unreasonable that peroxide might be in a solution.
It's quite reasonable, and yeah, I mean, in my own lab, I left samples in for days in the dark, monitoring, if there's any change in the activity level, and monitoring the beta spectrum quite closely.
Okay, yes?
To Professor Bachris, what was the difference between cell A and cell B?
The amount of exposure time. The one with the greatest tritium was exposed for something like 4.5 weeks. That exposed means constant charging at 60 milliamps per square centimeter. And the cell with the lower tritium was charged for a lesser time, and I'm not sure how much. I think it was 3 weeks. You?
My question is also to you, Professor Bachris. Given your comments earlier, in general in chemistry or electrochemistry, it's accepted that if we have the law of mass action, which dictates that if we have A plus B goes to C, as we raise the activity or the fugacity of either or both reactants, A or B, we generally drive the reaction to the right. Do you believe, my question is, do you believe that that same chemical sort of viewpoint would apply at all to a nuclear reaction of deuterium plus deuterium at high activity, 10 to the 12th, forcing a nuclear reaction of helium-3 or helium-4?
Well, I'll say my own common sense and intuition says yes, but I'm not really qualified to answer it by experience. Is that a Dr. Wolf question? No? You.
Stan Lockhart from MIT. I have a general question about fusion product measurements in these experiments. You know, we've heard a lot about positive and negative results today, and I think that's kind of a digital way of reporting the results. It's not quite correct. The real question is a quantitative one about